Welcome to Chapter 2. Welcome everyone to this session on Chapter 2 of your Radiation Safety Training. This chapter is titled Radiation, Radioisotope and Radioactivity. For anyone appearing for the RSO examination, this is where your journey truly begins. We are going to look at the basic science that make radiation happen. You do not need to be a nuclear physicist to understand this. We will break it down step by step so you can manage your safety programs with total confidence. What exactly is radiation? Let's start with a simple question. What is radiation? Think of it as energy on the move. It can travel in different forms as heat, as light, as tiny moving particles, or as invisible electromagnetic waves. Imagine a shaky, unstable atom. To become steady and stable, it needs to get rid of some extra energy. It throws this energy out in the form of fragments or bundles. That thrown energy is what we call radiation. The 20 electron volt golden line. Not all radiation is the same. We divide it into two groups based on how much punch or energy it has. The magic number to remember for your exam is 20 electron volt. If radiation has energy less than 20 electron volt, it is called non-ionizing. This includes things we use every day like the heat from a stove, microwaves that cook your food, or the visible light from your bulb. These don't have enough energy to break atoms apart. Understanding ionizing radiation. Now let us talk about the type that concerns us as RSOs. Ionizing radiation. This radiation has energy greater than 20 electron volt. Because it is so energetic, it can crash into matter and literally split atoms apart, knocking out electrons and creating charged particles or ion pairs. This process is called ionization. When we talk about alpha, beta, gamma and X-rays, we are talking about this powerful ionizing radiation. Meet the atom. To understand radiation, we must look at the atom. The atom is the smallest building block of any element. Whether you are looking at a piece of gold or the air you breathe, it is all made of atoms. Every atom has a very crowded, heavy center called the nucleus. Inside this nucleus are two main residents, protons, which carry a positive charge, and neutrons, which are neutral. Together, we call them nucleus. The orbiting electrons. If the nucleus is the sun at the center, the electrons are like planets revolving in their orbits. Electrons are very tiny. They weigh only about 1 divided by 1848th of a proton. Despite being small, they carry a powerful negative charge. In a normal stable atom, the number of positive protons equals the number of negative electrons. This balance makes the atom electrically neutral. Protons are the ID card. Here is a key point for your exam. The atomic number is just the number of protons in an atom. Think of it like a roll number or an Aadhaar card. It determines the atom's identity. For example, every atom with one proton is hydrogen. Every atom with 8 protons is oxygen. If you change the number of protons, you change the element itself. This is why the chemical properties of an atom depend solely on its atomic number. Atomic mass, the total weight. While protons give the identity, the atomic mass or weight is the total weight of the nucleus. Since electrons are almost weightless, we only count the protons plus the neutrons. Neutrons don't have a charge, so they don't change how the atom behaves chemically. But they do change how much the atom weighs. Isotopes, the family members. What happens if two atoms have the same number of protons but different number of neutrons? We call them isotopes. Think of them as brothers from the same family. They have the same name like hydrogen because they have the same number of protons but they have different weights. Because of the neutrons, hydrogen, for example, has 3 isotopes, H1, H2 and H3. They all have one proton but different weights. Radioisotopes, the Secchi atoms. Some isotopes are very stable, like a rock, but others are Secchi or unstable. We call these radioisotopes. Because the nucleus is unstable, it wants to change into something stable. It does this by ejecting or splitting out a piece of itself or releasing a burst of energy. This act of splitting out energy is what makes them radioactive. Natural versus synthetic. Nature gives us about 50 naturally occurring radioisotopes like radium-226 or uranium-238. But as humans, we have learned to make our own. Using machines called nuclear accelerators, we create synthetic man-made isotopes. A famous example is technetium-99m, which is used every day in hospitals for medical diagnosis. If an atom has an atomic number greater than 92, it is always man-made. What is radioactivity? We use the term radioactivity to describe the process of an unstable nucleus trying to become stable. It is a measure of how many atoms are disintegrating or breaking apart every second. When an atom decays, it doesn't just disappear, it transforms into a new element or more stable version of itself while releasing energy as particles or waves. Measuring the activity. How do we count radioactivity? We count how many disintegrations happens per second. In your work, you will see two main units. The older traditional unit is the Curie, named after Marie Curie. It is based on the activity of 1 gram of radium. The modern international unit is the becquerel, BQ. 1 becquerel is simply 1 disintegration per second. Converting Curies into becquerels. For your RSO exam, you must remember this conversion. 1 Curie is equal to 3.7 times 10 to the power of 10 becquerels. That is 37 billion disintegrations every second. Because Curies are such a large unit, we often use smaller versions like millicurie or microcurie in the lab. Alpha radiation, the heavyweight. Now let us look at the decay modes, the ways atoms spit out energy. First is alpha radiation. An alpha particle is like a heavy cannonball. It is made of 2 protons and 2 neutrons. It has a +2 charge and is very large. Because it is so big and heavy, it can't travel very far, only a few centimeters in the air. The alpha hazard. Because alpha particles are so bulky, they cannot even penetrate your skin or a thin sheet of paper. This means alpha is not an external hazard. However, if you accidentally breathe it in or swallow it, those cannonballs will hit your internal cells directly. Therefore, we treat alpha as a very serious internal hazard. Beta radiation, the fast electron. Next is beta radiation. This is a light, fast moving particle. A beta particle is actually an electron that is ejected from the nucleus when a neutron transforms into a proton. It has a negative charge. Because it is much smaller than an alpha particle, it can travel further up to a few meters in the air and can penetrate slightly into your skin. Gamma radiation, the invisible wave. Third is gamma radiation. Unlike alpha and beta, gamma is not a particle. It has no mass and no charge. It is a high energy electromagnetic wave, just like light or radio waves, but much more powerful. It travels at the speed of light and originates from deep inside the nucleus. The power of gamma penetration. Because gamma rays have no mass, they have a very low chance of hitting anything as they pass through. This makes them highly penetrating. They can easily pass through your body, through wood, and even through thin metal. To stop them, you need very dense materials like lead or thick concrete. X-rays, the electronic cousin. You might wonder, are X-rays different from gamma rays? Physically, they are identical. They are both light like wave. But the only difference is their home address. Gamma rays come from the nucleus, but X-rays come from the electrons outside the nucleus. We usually produce X-rays by crashing fast electrons into a metal target in a vacuum tube. Neutron radiation. A fourth type you should know is neutron radiation. As the name suggests, this is the release of neutral neutrons from the nucleus. You won't usually find this in a small hospital labs. It is mostly encountered in nuclear power plant reactors or in medical cyclotron. Because they have no charge, neutrons are also very difficult to stop. Summary of the decay modes. For your exam, remember this comparison. Alpha and beta emissions form new elements because they change the number of protons in the nucleus. However, gamma emission is just a release of energy. The element stays exactly the same. Think of it like an atom trying to release stress. The concept of half-life. How long does radioactivity last? We use a term called physical half-life. This is the time it takes for exactly one half of the radioactive atoms to decay away. Every isotope has its own unique clock. For example, iodine 131 has a half-life of 8 days, while carbon 14 takes 5700 years. Calculating remaining activity. As an RSO, you must be able to calculate how much radiation is left after some time. We use the formula activity at time t equals initial activity times e to the power of negative lambda times t. Don't let the math scare you. Lambda is just a decay constant calculated by dividing 0.693 by the half-life. If you know the half-life, you can predict the future of your source. Why this matters for the RSOs? In conclusion, why did we learn all this? As an RSO, you are accountable for every source on your license. You must know if your source is an internal hazard like alpha or an external hazard like gamma, so you can choose the right shielding. You must track your inventory using half-life calculations so you never exceed your legal limits. Understanding the science is the first step to keeping everyone safe.